organize what we will learn in this class. Okay, so far after our midterm, we already reviewed and we know some theories about EM field. EM field. This is chapter 1. If you have any question, you can check your book. Okay. So now you have some concept about EM field. Those fields, probably you will apply this theories to antennas. Antennas is 天线, okay? Because this is wireless communication. As I said, you can apply this theories to chapter 2, which is the transmission line, high microwave transmission line. In microwave transmission line, we use voltage and current instead of E field and H field. But in this part, we are talking about, we just use the figures. This is just a figure. This is a very ideal case of the transmission line. This is what we do for chapter 2. Okay? For chapter 3, we try to apply the theories in chapter 2 to 3 different kinds of transmission lines. The first one is coaxial cable. Coaxial cable. The second one is micro strip line. This is what, when you design circuit, you use a lot of micro strip line. And also waveguide. Okay. These 3 different types of high frequency transmission line, all of them can apply the theory in chapter 2. Okay. This is a theory, and chapter 3 are the applications. Okay? Okay. For chapter 3, what are the difference between chapter 2 and chapter 3? For chapter 3, for 3 different kinds of the high frequency transmission lines, they have different equation for beta. They are all different. Which one is most? Which one is simplest? Which one? This one. Coaxial cable is simple. Why? Because for coaxial cable, the lowest mode, the fundamental mode for this cable is TEM mode. So you can use the simplest equations from chapter 2 to obtain the coaxial cable. This is the easiest. And this is the numerical method beta. Because the microstrip line is different, this is not TEM mode, this is quasi-TEM mode. We will have more explanation when we are in chapter 3. For the last part, waveguide, this is the most complicated, because for the waveguide, this kind of transmission line, they don't have TEM mode. They have only TE mode and TM mode. It is very, very complicated, and this is a single conductor transmission line, no TEM mode, and you will have many maths for the waveguide. Okay, so this is chapter 3. Chapter 2, we apply the theory of chapter 1 to understand. You will feel this is easier than chapter 1 because we have only voltage and the current. You don't need to write down the vector. You don't need, because just the voltage and the current. At least you just think about a positive or negative. That's it. This is not the vector. You don't need to consider a lot about vector because we consider two-dimensional. So one-dimensional or two-dimensional. Just only on a line. We try to calculate our voltage and the current only on this cable. So this should be much easier. Okay? For the last part of chapter 2, we will discuss about the Smith chart. This is a very important tool when we try to deal with the microwave transmission line. Okay? So those are the contents we are trying to explain in this class. And if we have more time in this class, maybe I will buy you more things, such as chapter 4, we will talk about S parameters or ABCD matrix. If we don't have time, maybe we just give this to the lab class for the next semester, okay? And after you do that, there are a lot of the circuit design, very similar to what you are doing in the practice, the 专题, okay? You try to design different kind of circuit, such as the power divider, okay, or a couplers, or maybe filters and amplifier. Okay. To design filters, you will need more concept before design filters, because you will use your transmission line to see this transmission line like resonators. Okay, so you will understand resonators, and there will be more concept about if we want to design filters. Okay. Okay, and I think all of you already have some concept about how many circuits you are going to learn in this field in the 射频无线通讯系统. You already know there are many circuits. Okay, so we will come back to chapter 2 to understand. And I hope we will have more activities, and you can evolve to get more points. Okay, especially if you don't get good points, good score in the midterm, maybe you can get good score when I ask questions. Okay, you still have opportunities. All right. So let me just simply review
some content I already introduced for the beginning of the chapter 2. Okay. To understand the high frequency transmission line, we will try to explain the transmission line theory. The theory starts from we treat this transmission line, this uniform transmission line, the ideal high frequency transmission line model. We treat this line as a lot of sections. We cut this transmission line to many, the infinite numbers of small pieces, okay? And which pieces of the transmission line can be treated as this model, okay? This is a lossy transmission line. We have R and G. Those are the component if you got loss. If it is lossless, R and G, they are 0. Okay. Okay. So the beginning to derive the telegrapher equation is we treat the transmission line, we treat all kinds of the high frequency transmission line as this ideal model. There are many pieces of this short, very short, extremely short transmission line. Each section of this model has a length delta 0 close to 0. So each piece is very small. So we just write down, we try to, first of all, we define the input current and input voltage and the output current and output voltage for each pieces. Then we apply the Kirchhoff's voltage law. The input voltage equals to the voltage close to the resistor and close to the inductor and also close to and plus the output voltage. Okay? So you can obtain the input voltage equals to this, the summation of these three voltages. This is the Kirchhoff's voltage law for the first equation. Similarly, we apply the Kirchhoff's current law. The input current will equals to these three current. Okay, so each current, the equation for each current, each part can be written down as these three portions, three parts. Okay? Then we use these two equations and we set the delta z to 0. Then we can get the limit. Then we obtain these two equations. Okay. These two equations are telegrapher equations, which is very similar to the E and the wave, those wave equations we derive in chapter 1. Okay? This is the first part. So when we derive the EM, when we obtain the result from the electric field and H field. The first step we do is we try to operate the curve to both of the equation. So we did the same thing to the telegrapher equations. So we can obtain, we take the partial respect to z to both of these two equations. Then we can obtain these two results. Okay? See? From this, these equations, let's go back to here. These two equations are the telegrapher equations. Okay? For the voltage, this is a voltage everywhere, every time on this transmission line, the voltage, and this is the current at any time. This is a function. The voltage is a function of position and the time. The current is also a function of position and the time. Okay? For the first equation, you take the partial of your position to your z will equals to minus r. What is r? Can anyone give me answer? This will get you 5 points. What is r? Tell me what is r? 5 points. Just raise your hands. Okay? Not exactly. Just you need to give me the strict, the complete answer about r. Series, I need, it's not accurate. Is that all? I want you to explain more. 5 points. What is R?
Resistance per unit
Length. Yes, correct. 5 points. This is not resistor. This is the resistance per unit length. This is the average. It's like an average, but it is uniform. So it's supposed to be the same. Okay. But if this is the non-uniform transmission line, R will be a function of Z. If this is a non-uniform transmission line. But for our easy case in chapter 2 and chapter 3, they are just a constant because this is not changing. R will equal to something. That's it. Okay? Similarly, L, C, and G, they are 4 numbers, 4 values. All of them are the values for unit length. Okay? Just you need to remember that. This is different. Resistance and the resistance unit per unit length, they are different. Okay. So, this part will equals to minus R times the current everywhere and anytime minus L times I take a partial differential to the T. It is time. Okay? So you need to pay attention on that. this is the partial respect to position, and this is the your current will take the partial to time. Okay? Okay. So this is different. Can anyone tell me that? Can we simplify this? 2 points. 2 points. It's easy. If you take the partial to time, what's that? For this part, anyone raise your hand? Can we simplify this time if this is a time harmonic? What? Just raise your hand. No. Can we simplify this one? If I take the partial to time, what can we change this term? We did this one in EM field. Do you remember anyone? We did the same thing before, but in this term, we can do the same thing because this is time harmonic. If this is time harmonic, equation is minus j omega t. So we have this term. Yeah, anyone? So if we take this one respect to time, what can we obtain? J omega, let's say J omega. Yeah, you can change this to J omega I, yes. Okay, 2 points. Okay, let's take a rest.